One of the primary functions of the kidney is better understood at the level of the nephron. In forming urine, the nephron functions to remove metabolic wastes from blood while regulating the volume and composition of body fluids. Urine formation begins in the renal corpuscle, where blood passing through the glomerulus is filtered. Filtrates include water, ions, and other solutes, which are filtered out of the blood and into the capsular space to begin urine formation. Urine passes into the proximal convoluted tubule, then into the nephron loop. The nephron concentrates urine by the process of the countercurrent multiplication system. The countercurrent multiplication system is basically the means by which water and sodium are extracted from the filtrate as it passes through the tubules toward the collecting ducts. This system is called countercurrent because of the dynamics set up by the hairpin turn of the loop of Henle. The direction of flow in the descending limb of the loop is opposite from the direction of flow in the ascending limb. By flowing in opposite directions in such close proximity, a unique interaction occurs. The loop of Henle dips from the cortex of the kidney into the medulla and is surrounded by the medullary interstitial fluid. The countercurrent multiplication system is responsible for not only elevating the concentration of urine in the loop, but more importantly, it elevates the concentration of the interstitial fluid as well. To explain the countercurrent multiplication system, we must first imagine the loop filled with a stationary column of glomerular fluid, which includes water, salt, and urea. At first, the concentration of the glomerular fluid and the surrounding interstitial fluid will be equal at an osmolarity of 300 milliosmoles. Within the walls of the thick segment of the ascending limb, special pumps extract salt, sodium chloride, from the fluid and transport it to the interstitium. The two areas no longer have an equal osmotic pressure and a gradient has been established. Within the thick segment, the concentration is at 200 milliosmoles, whereas in the medullary tissue, the concentration is at 400 milliosmoles. Over time, a net diffusion of salt into the descending limb and a net diffusion of water out of the descending limb results in a balance in osmolarity between the descending limb and the surrounding interstitium. Because the thick segment is still actively pumping out salt, the osmolarity of the ascending limb is still 200 milliosmoles, and the interstitium and descending limb are balanced at 400. Salt accumulates in the medulla while water is drawn out of the fluid in the descending limb. Water is removed by the vasa recta, which are capillaries that surround the loops. In real life, operation of this gradient occurs while the fluid is flowing. Fluid flowing in from the proximal tubule and out to the distal tubule along with the constant pumping of salt into the medulla contributes to the multiplication of this gradient. As fluid follows the path of the loop, an increasing amount of water is extracted as it reaches the bottom, and an increasing amount of salt is pumped out as the fluid reaches the top. The more salt pumped out, the higher the concentration in the medulla. The higher the concentration in the medulla, the more water is extracted. Eventually, the levels of osmotic pressure are equal horizontally, with the highest value being at the tip of the loop. This level is at 1,400 milliosmoles per liter, which is also the value of the maximal osmolarity of excreted urine. As you can see, fluid becomes more concentrated as it rounds the loop, but it immediately becomes rediluted as it reaches the top. Final concentration of the fluid occurs in the collecting ducts as it must travel back through the concentrated interstitium of the medulla on its way to the calyces. Urine is concentrated even further in the collecting ducts. The collecting duct must transport urine back through the concentration gradient formed by the nephron loop. The walls of the collecting duct are permeable to water, but not to salt. Therefore, an increasing amount of water is drawn out by osmosis as the fluid travels through the gradient. The gradient provides the force for the concentration of urine, but the rate is determined by the amount of antidiuretic hormone, ADH, in the blood. An increase in ADH in the blood causes the collecting ducts to become more permeable to water. Less urine is secreted and it is more concentrated. A decrease in ADH results in a decrease in water removed, thus a larger volume of more dilute urine is excreted.